Hello everybody, welcome again. I am Ramesh Bhuya from Dev Study. In this presentation, you are going to learn a very simple and shortcut method to derive Gibbs Helmholtz equations and also the utilities of Gibbs Helmholtz equations in different processes and chemical reactions. First of all, the derivation of Gibbs Helmholtz equation. Let's a system in state 1 having entropy S1, free energy G1 and enthalpy H1 undergoes a change at constant pressure and temperature to another state, namely state 2 with entropy S2, free energy G2 and enthalpy H2. From the definition of Gibbs free energy G, we know that G is equal to H minus Ts. Therefore, for state 1, G1 is equal to H1 minus Ts1, equation 1, and for state 2, G2 should be H2 minus Ts2, equation 2. Now, by equation 2 minus 1, we can write G2 minus G1 is equal to H2 minus H1 minus T H2 minus S1. Therefore, G2 minus G1, that is delta G, is equal to H2 minus H1, that is delta H, minus T H2 minus S1, that is T delta S. Therefore, delta G is equal to delta H minus T delta S, equation A. This is the Gibbs Helmholtz equation. First, that is, it is one of the form of Gibbs Helmholtz equation. Again, dg is equal to dp minus sdt. This is very important thermodynamic equation. At constant pressure, dp should be 0. Therefore, del G del P at constant P is equal to minus S. So, for state 1, del G1 by del T at constant P is equal to minus S1, equation 3. And for state 2, del G2 by del T at constant P is equal to minus S2, equation 4. Therefore, by equation 4 minus 3, we can write del G2 by del T at constant P minus del G1 by del T at constant P is equal to minus S2 minus S1, or del G2 minus G1 del T at constant P is equal to minus S2 minus S1, that is minus delta S. Therefore, del of delta G, G2 minus G1 means delta G, by del T at constant P is equal to minus delta S. Therefore, delta S should be minus del of delta G by del T at constant P. Putting this value in equation A, we get delta G is equal to delta H minus T delta S. This is equation A. If we replace delta S by this minus del of delta G by del T at constant P, then this equation A becomes delta G is equal to delta H plus T del of delta G by del T at constant P. This is equation B. This is another form of Gibbs Helmholtz equation. So we get two types of Gibbs Helmholtz equation. This is one of the form of Gibbs Helmholtz equation. This is another form of Gibbs Helmholtz equation. Again, del of delta G by T by del T at constant P is equal to, first 1 by T remain constant, del of delta G by del T at constant P. Then delta G remain constant, del of 1 by t by del t at constant p, which is minus t square. Therefore, minus delta g by t square. Therefore, 1 by t square into t into del of delta g by del t at constant p minus delta g. Now, t into del of delta g by del t at constant p can be replaced by, from equation b, delta g minus delta h. So this term can be replaced by delta g minus delta h, applying equation b. Now this delta g and this delta g can be cancel each other. Therefore, del of delta g by t by del t at constant p is equal to minus delta h by t square, equation c. This is another form of Gibbs Helmholtz equation. So we get three forms of Gibbs Helmholtz equations, namely delta g is equal to delta h minus t delta s, equation a. Delta g is equal to delta h plus t into del of delta g by del t at constant p, equation b. And del of delta g by t by del t at constant p is equal to minus delta h by t square, equation c. Here these three equations, equation a, equation b and equation c, are known as Gibbs Helmholtz equations. Now, application of Gibbs Helmholtz equation. Gibbs Helmholtz equation is given by delta g is equal to delta h minus t into delta s. Applying this and knowing the values of delta h and delta s at different temperature, we can easily calculate the value of delta g at different temperatures of a process or chemical reaction. So, delta g can be calculated from this relation of a process or chemical reaction at different temperature. We know that if delta g is negative at a particular temperature, then the process or chemical reaction will be spontaneous. And if the value of delta g becomes positive at a particular temperature, then at that temperature the process or chemical reaction will be non-spontaneous. That is, the process or chemical reaction does not occur at that temperature. Therefore, we can conclude that we can predict the spontaneity of chemical reaction or process at different temperature using this Gibbs Helmholtz equation. For example, in the combination reaction of NH3 and HCl to form ammonium chloride NH4Cl, the reaction is given by NH3 plus HCl is equal to NH4Cl plus heat. As heat is given out during this reaction, combination reaction, so the reaction is exothermic. Therefore, as the reaction is exothermic, delta G should be negative quantity. In this reaction, number of molecules decreases. NH3 plus HCl is equal to NH4Cl. That is, two molecules combine to form a single molecule. And hence, the degree of randomness decreases. Therefore, entropy of this reaction should be decreases. That is, delta S should be negative quantity for this reaction. Now, from Gibbs Helmholtz equation, we know that delta G is equal to delta H minus T into delta S. At low temperature, the value of mod of delta H should be greater than the value of mod of T into delta S, since the value of T is low at low temperature. Now here both delta H and delta S are negative. Therefore, using this relation, we can say that at a low temperature, delta G should be negative quantity. Therefore, at a low temperature, this combination reaction will be spontaneous. The combination reaction will be spontaneous at low temperature. On the other hand, at high temperature, the value of mode of delta H should be less than that of T into delta S, because the value of T is high, and as in this reaction delta H and delta S both are negative, therefore using this relation we can calculate the value of delta G at higher temperature, and it should be positive quantity, as both delta H and delta S are negative and T is high, therefore T del S should be greater than delta H. So at high temperature, this combination reaction will not occur. That is, at the combination reaction does not occur at high temperature. On the other hand, if we take the reverse reaction, that is the dissociation reaction of NH4Cl to form NH3 and HCl. The reaction is given by NH4Cl plus heat is equal to NH3 plus HCl. In this reaction, heat is absorbed during the dissociation process. As heat is absorbed during the reaction, so it is an endothermic reaction. Therefore, as the reaction is endothermic, delta H should be positive quantity. Since number of molecules increases in this reaction, one molecule of NH4Cl dissociates to one molecule NH3 and another molecule of HCl. That is, one molecule is dissociates to two molecules, and hence the degree of randomness increases. As a result, entropy should be positive for this reaction, that is delta S positive quantity for this reaction. Therefore, in this reaction, both delta H and delta S are positive quantity. Now, Gibbs Helmholtz equation, we know that from Gibbs Helmholtz equation we know that delta G is equal to delta H minus T into delta S. At low temperature, we know that the value of delta H should be greater than that of T into del S, and as delta H and delta S both are positive, therefore at low temperature delta G should be positive using this relation, and hence at low temperature the dissociation reaction will be non-spontaneous, that is does not occur at low temperature. The reaction is non-spontaneous at low temperature. On the other hand, at high temperature, mode of T delta S should be greater than that of delta H, as T is high, and as delta H and delta S in this reaction both are positive, therefore using this equation we can predict that the value of delta G at high temperature should be negative for this reaction, and hence the reaction will be spontaneous at high temperature. Therefore, application of Gibbs Helmholtz equation can be generalized for different types of reaction as in the following table. For those reactions in which delta H is positive and delta S also positive, that is both delta H and delta S are positive, using the Gibbs Helmholtz equation at low temperature T del S should be less than that of delta H. Therefore, the value of delta G should be positive. That is, at low temperature this type of reaction will not occur. That is non-spontaneous. With increasing temperature, the value of T del S increases, and hence at a particular temperature the value of T del S should be equal to delta H. That is, at that temperature delta G should be 0, and hence the reaction will attain equilibrium at that temperature. After equilibrium, if we increase the temperature, then T del S should be greater than that of delta H. That is, delta G becomes negative. So, after equilibrium, if we increase the value of temperature, then the value of delta G becomes more negative. Therefore, after equilibrium, the reaction will be spontaneous. In the second kind of reaction, in which delta H is positive and delta S is negative, at low temperature, as T del S is less than delta H, so delta G should be positive, that is non-spontaneous. And also at higher temperature, the value of T del S increases, but as del S is negative, so at higher temperature also delta G becomes positive, and with increasing temperature the value of delta G increases, the positive value of delta G increases. So at higher temperature also the reaction is non-spontaneous. Therefore, for this type of reaction, that is delta H positive and delta S negative, the reaction is non-spontaneous at any temperature, that is low temperature as well as at high temperature. For the third kind of reaction, in which delta H is negative and delta S is positive, using this equation, as delta H is negative and delta S is positive, at low temperature we know that delta H greater than T into delta S. So according to this relation, the value of delta G becomes negative at low temperature, so the reaction is spontaneous. And at high temperature, the value of delta S increases, that is T del S also increases, that is the negative value of delta G increases with increasing T. Therefore, at a low temperature it is negative, and as well as at higher temperature it will be negative, and with increasing temperature the value of delta G increases negatively. The negative value of delta G increases. Therefore, the reaction is spontaneous at low temperature, and with increasing the value of temperature the reaction becomes more spontaneous. For the fourth kind of reaction, in which both delta H and delta S are negative, at low temperature the value of T del S is less than that of delta H, therefore delta G becomes negative, that is the reaction becomes spontaneous. With increasing temperature the value of T del S increases, and at a particular temperature the value of T del S becomes equal to delta H, that is delta G becomes 0. So the reaction will attain equilibrium at that temperature. Further increase of temperature increases the value of T delta S, and as delta S is negative, so this term becomes positive, and overall the value of delta G becomes positive. So after equilibrium with increasing temperature, the value of delta G becomes more positive, that is non-spontaneous. Therefore, we can predict the spontaneity and equilibrium of a reaction at different temperature by Gibbs Helmholtz equation. That's all for today's. If you have any question, please write in the comments. If you like the video, please share to watch others. Must subscribe our channel to watch videos like this. Thank you. Bye.